Okay, so in this video, we're going to talk about free energy. Okay, now when it comes to free energy, two main terms or vocab terms kind of come to mind: spontaneous and non-spontaneous process. All right, so a spontaneous process is a process of or reaction that once it gets started, it proceeds on its own without any external influence, while a non-spontaneous process takes place only in the presence of a continuous external influence. All right. Now let's not get spontaneous confused with the normal English definition of something that's spontaneous, right? So the normal English definition of something that's spontaneous is something that happens very, very quickly. But in chemistry, we use that term very, very differently. And spontaneous simply means that no needed or added external influence. Well, I'm saying this all wrong. It doesn't need an external influence for the reaction to continue to take place or the process to continue to take place. Once it gets started, it just kind of goes on its own. All right. And so that tells us that it's a spontaneous process. Like, for example, if you're burning a candle wick, once you could get the flame going, right, you don't need to do anything else for the wick to continue to burn. So that process there is a spontaneous process. All right. And then a non-spontaneous process is something that always needs an external influence for the process to continue to take place. Okay, so that's kind of the big thing on that one. Okay, now one big idea that we need to address when it comes to free energy or spontaneous processes is the idea of entropy. All right, or other words, S. All right, so entropy is the measure of the amount of molecular disorder in a system. All right, and so the units of it could either be calories per mole Kelvin or joules per mole Kelvin. All right, now there's essentially two ways that you could affect the entropy of a particular substance. All right, and the two ways are essentially is the state of matter, all right, and the number of moles in the system. Okay, so what do I mean by that? So let's first look at the state of matter and how entropy could be affected. All right, so let's just say, for example, you start off with solid ice, right? So here's ice. So we're talking about H2O here. All right. And in solid ice, we get to the point where we're liquid water. Okay. And then lastly, I know I'm doing this very quickly. Here's fire. All right. And then we have steam. Okay. So what's happening here? Here, as you move this direction, entropy is increasing. Okay, why is that? Well, in the solid state, remember, entropy is all about the measure of disorder in the system. Okay, and so when you have a substance in a solid form, the molecules are very organized. All right, so entropy is very, very low, or sometimes it's a negative number. All right, and so that just tells you when you have entropy, especially when it's a negative number, that simply means it became more orderly, or it's something that has an order. Okay, and then as you move towards the right, as a solid becomes a liquid, all right, it's not as organized. You're breaking some of the intermolecular bonds. They're rotating, vibrating, moving past each other, and so on and so forth when it comes to the molecules in the liquid state. But then when you heat it up even more, you add more energy to this, then all of a sudden you're at the gas state. Gas state, very, very high entropy, very, very disordered. All right, gases are literally everywhere, moving in all sorts of different directions in complete random motion. Okay, so that's That's one way that you could affect the entropy of a particular substance is by changing the state of matter. Another way that we could look at this is due to chemical reaction. Throughout the chemical reaction, does it become less ordered or more disordered? Okay, and so let's kind of look at this so you can see exactly where I'm coming from in this case. And so, like, for example, if we have this reaction where it's 2H2 plus O2 yields 2H2O. Okay, so how do we, when we look at this reaction, how do we know if it becomes more ordered or more disordered? Well, basically what we do is count how many moles we have in each side. All right, so on the reactant side, I have 3 moles of substances. Okay, on the product side, I have 2 moles. Now, because the number of moles essentially decreased, all right, because it decreased as you've gone this way, entropy, or S, actually decreases as well. All right, because you're going to from more moles to fewer amount of moles. When you have fewer amount of moles, it's typically more organized. When it's more organized, your delta S is negative. All right, that change from disorganization to organization, S will make it that it's a negative number, and so thus you can see that it has been more organized. All right, so just to reiterate, there's 2 ways really changing the entropy of a particular substance. It's either you change the state of matter. So if you're going from gas, liquid to solid, right, you will see that substance becoming more and more organized. Entropy in this case, delta entropy. All right, let me state that delta S, not a highlighter. All right, delta S in this case, if you're going from gas, liquid to solid, delta S in this case would be a negative number, because as you're going from gas, liquid to solid, the molecules are becoming more and more organized. Okay, versus if you go the opposite direction, then delta S would be a positive number. Okay, and then the other way we could kind of look at it, if you look at the overall chemical reactions and look at the want to look at the mole ratios. All right, and so see here, the example I've given you here is that you start off with 3 moles of reactants, but then turn out with 2 moles of products, and so things became more organized because of the chemical reactions. So thus delta S decreased, or delta S would be a negative number. All right, so ultimately there are 2 factors that affects if a process or a chemical change or physical change is a spontaneous process. All right, there's 2 things that affects it. All right, so the first thing is entropy, and we kind of talked about that, so S. And the second thing that affects it is enthalpy. All right, or other words, H, or the amount of the heat of the process. Okay, and so these 2 things affect how spontaneous something may be. Okay, now in order for the process to always be spontaneous, both enthalpy and entropy has to be favorable. All right, and for entropy to be favorable, all right, so I'm gonna kind of jot this down here. So for it to be favorable, delta S must be a negative delta S, or actually, I'll take that back. It must be a positive delta S, and it should be a negative delta H. All right, so positive delta S and negative delta H for if you're talking about favorability of a spontaneous process. Now, for the process to be considered non-spontaneous, all right, you want these things to be unfavorable. So an unfavorable entropy is one that is a negative. All right, so it's becoming less disordered. All right, another unfavorable for enthalpy is when it is gaining energy. All right, so anything that's gaining energy, it's unfavorable in terms of enthalpy. Okay, so if you have a particular process, whether it be physical or chemical, the process where both the entropy and the enthalpy are favorable, then this process is spontaneous. All right. This is a spontaneous process. Okay. And that's if this process both have a positive delta S and a negative delta H. Okay. Now, if the process have unfavorable conditions when it comes in terms of entropy and enthalpy, so entropy is a negative delta S and enthalpy is a positive delta H, then this process is non-spontaneous. All right. And that's always going to be the case, regardless. Now, it is possible where you may have processes where you may have a favorable delta S, but a unfavorable delta H, all right, and it turns out to be spontaneous. Okay, that could happen. And the flip side is also true, where there are some processes where, it's favorable in terms of enthalpy, but unfavorable in terms of entropy, and then that process is still spontaneous. So how do we know, in what scenarios can it be spontaneous, and what scenarios that even if this is the case, that it may not be spontaneous? All right. And we figure this out due to the measure of what we call Gibbs free energy. Other words, G, or delta G. Okay. And so Gibbs free energy is a measure of the change in free energy as a chemical reaction or a physical change occurs. All right. And so Gibbs free energy is often calculated as a delta G is equal to the delta H minus T delta S. All right. Where delta H is your enthalpy, okay, or the heat of reaction. Delta S is your entropy, and then T here is temperature, but specifically it needs to be in kelvins. All right. So delta G takes into account of these two factors that affects if it's going to be spontaneous or not. Okay. And so when we're looking at delta G specifically, right, once we could use those two factors as enthalpy and entropy to help us figure out delta G, or figure out the change of free energy, or the free energy change, whatever, then we could either figure out if the process is exergonic, or other words, is it spontaneous, or if it's endergonic, meaning the process is non-spontaneous. Okay. So how can we figure out, by looking at the delta H's and delta S, will the process be spontaneous or not? And it's basically by the sign of G. Okay. And so an exergonic or spontaneous process, delta G will be a negative number. Okay. An endergonic or a non-spontaneous process, delta G will be a positive number. Okay. Now, depending on the values of delta H, T, and delta S, then we could easily calculate and figure out if the reaction is going to have a negative delta G. All right. And so let's kind of break this down so you can see exactly what I mean by this. All right. So let's kind of view and see what must take place in order to make sure that you have an exergonic or a spontaneous process. And so if both delta H and delta S are favorable, meaning that delta H is negative, delta S is positive, delta G will always be negative. Always. Okay? Be negative. And this could easily take place in all temperatures. So it doesn't matter what temperature, if the case this process is in. As long as delta H is negative, delta S is positive, and regardless of the temperature, delta G will always be negative. What does that mean? That means it's exergonic. All right. It's spontaneous. All right. This process doesn't need any external influence for it to continue to do its thing. Okay. Now, what if everything was unfavorable, right? If delta H was positive, if delta S was negative, delta G will always be positive, always, at all temperatures, regardless. All right. And so in this case, you have an endergonic process. All right. So this reaction is non-spontaneous at all temperatures. Now, let's say we have some type of, we mix match this just a little bit. All right. So let's just say if our delta H was positive. Yeah, when it's positive, remember it's endothermic. Okay. So this case was endothermic as well. This case was exothermic. Okay. It's endothermic. Okay. Here, it's positive. That means more disorder. All right. Just like this one was more disorder. This one here was less disorder, or became more ordered. All right. Now, what happens? Well, delta G, it kind of depends, okay? But if we're talking about spontaneous, and we're only looking to spontaneous reactions, okay, then it really depends at the temperature, at what point we'll get a spontaneous reaction. And so in order for it to be spontaneous, you must have high temperatures only, okay? That's the only way that this is going to be spontaneous. So there's a temperature threshold, okay? And it kind of makes sense if you think about the equation in of itself, right? And so your delta H is positive, all right? These two together is going to be a negative number. And you want delta G to be negative. So if you want delta G to be negative, then you want to make sure that the magnitude of this number is higher than that of delta H, especially if delta S is a positive number. All right. And so because delta S is a positive number, your temperature needs to be high. So that way, when you multiply these two numbers together, the magnitude of the product of these two numbers is higher than delta H. All right. And if that's the case, then you will have a delta G that's negative. Okay, so looking at the equation, hopefully that kind of makes sense, right? And so the opposite is also true. So if your delta H is negative, meaning that it's an exothermic process, okay, and then your delta S is also negative, meaning that it's less disordered. So the process becoming more and more ordered, less chaotic. All right. Now, if you want delta G in this case could either be positive or negative. It just kind of depends, right? But if we want it to be negative, so we're focusing on the negative part. If you want it to be negative, then this only takes place at low temperatures only. Okay. And as I said, that should kind of make sense. All right. Because if you think about this, your delta H is negative, right? Your delta S is also negative, all right? And so what happens is, because delta S is negative here, and you got this negative here, or this minus sign, technically is negative, right? It's a -1 here. When you multiply these two numbers together, you're going to get a positive number, all right? This positive number is going to counteract against this negative delta H. And so temperature has to be small to make sure that the magnitude of this number, because this is going to turn to a plus sign, the magnitude of this number is going to be smaller than the magnitude of delta H in order to make sure that delta G remains a small number, all right, or a negative number. I'm sorry, all right? And so That's the way you kind of have to look at this to see if something is endothermic or exothermic. I mean, endogonic or endergonic. All right, endergonic or exergonic. I'm sorry, or to look at the signs of delta G. All right. So a couple of things to keep in mind when you're looking at this. Remember, spontaneous process proceeds without any external assistance, and it's exergonic. All right. So meaning free energy is released and delta G is negative. Remember, spontaneous has nothing to do how quickly the process takes place. It's just a matter of fact that the process could take place on its own, okay? While a non-spontaneous process requires continuous external influence, all right, and it is endergonic, all right? So that means the free energy is being added and delta G is a positive value. The value of delta G for the reverse of a reaction is numerically equal to the value of the delta G of the forward reaction. All right, so if you look at a chemical reaction, you flip it, delta G, that number, the magnitude will always remain the same. You just have a different sign. All right, one's going to be negative, the other is going to be positive. All right, and just like I was showing you earlier in this chart here, depending on the values of your delta H and delta S, especially if one of them is unfavorable and the other one is favorable, then what will cause a reaction to go from non-spontaneous to spontaneous will be a change in temperature. Okay, and so this is Gibbs free energy.